Okay, so I'm going to talk about some of my experiences in the competition and talk about a particular technique for blending the results of a large collection of models into one overall prediction that's more accurate than any of the individual models. But I'm going to start off talking about just how I came to be on one of the leading teams and how that blending technique sort of got me on the team. But first, let me just start off. Well, I guess you just heard a lot of this, so I'll skim over it quickly. But yeah, so I was in Chicago. I just moved to San Francisco, and I'm a consultant on my own right now. Yeah, I got a PhD from Caltech, and the focus of that was machine learning. And actually, my first job out of grad school was actually right here in Mountain View. I was at NASA Ames, and I was sort of a computer science postdoc there for a little while. And then I worked in the dot-com world at a little startup that probably no one remembers. Their name was Ripfire, and they got bought by Plumtree, and they got bought by BA, and they got bought by Oracle. So maybe there's like some one line of code in Oracle that is from me still. But so then I got I moved over to the finance world, and I was what they call a quant, a mathematical modeler at a hedge fund out in Chicago, and did that for about 4 years, but I got kind of burnt out on that. Fortunately, I left before things got really nasty in the fall of 2008, so that wasn't entirely my fault, I don't think. So I quit that, and they actually, it was pretty nice. They actually paid me not to work for a while, so I was on a sort of this non-compete agreement, and I had some time, and I was just kind of pondering my next move, and I wanted to keep my skills sharp, and so I decided to give the Netflix prize a try. So that's how I got into it. So I want to start off by just acknowledging, like, this is not just my own work. There were definitely some collaborators here, one of which was Gabor Takacs, who he was actually the captain of the Ensemble, which was the second place team in the Netflix competition. And I've actually never met Gabor face to face. But I still feel this strong bond with him because we worked very intensely all over email. So he was just in Hungary the whole time, and even at the award ceremony in New York, he didn't get a chance to come out, which was sort of a shame from my perspective. I'm not even sure I'm saying his last name correctly, actually, but I still feel this connection. And then Lester Mackey he's a grad student at Berkeley, and he was also one of the leading members of our team, and actually he was on some previous teams and came very close to winning some of the earlier progress prizes, intermediate prizes that Netflix gave out as well. And David Lin was also a collaborator who worked closely with Lester. And I also want to acknowledge my girlfriend, Rachel, who's here tonight. So while I was working on Netflix, I did not have a job, and I wasn't really looking for one, and that's usually not very appealing to girlfriends. But she was very supportive to me, so I appreciate that. So I definitely appreciate that. And actually, I should mention, Stan Lanning was one of the guys who ran the competition from Netflix is here tonight, and I thought it was really like a flawless competition, so I appreciate that as well. So let me just start off just by explaining how Netflix works. I suspect the majority of you have a Netflix account, but some of you may not. So let's see, the laser pointer work. So yeah, I mean, this is an actual page from that's generated when I'm using my own account here, and here it's trying to recommend movies to me. And as you browse around and look at the movies that it's recommending, you can see underneath they have these 5 stars here, and that's so the amount of stars that are filled in is some sort of prediction of how much they think I'll like that movie. And as you know, since they're recommending them, most of these are sort of filled up towards 4 and 5 stars. But then as you browse around, if you see something that you've already seen before, like for instance, I actually did used to watch 6 Feet Under on HBO, but the Netflix system doesn't know that because I haven't told it that. But when you see something that you've already seen before, you can say, oh yeah, I've seen that, and this is how much I liked it. And you can click on any of these stars here. And I enjoy 6 Feet Under, so I probably would give it a 4 or a 5. But then as you do that, the system collects data on your preferences. And so for a long time, Netflix had some sort of machine learning system to generate predictions from that data. But around about 2005, 2006, they decided to just sort of throw it open to anyone to see if you could improve what they had. And so that was what the Netflix Prize was about. So it started in the fall of '06 and then ended a little less than a year ago. And so the training set that you got that you could download was about 100 million data points. And then what your task was to build a model to predict what the customer ratings of the movies would be on a test set of 1.4 million data points. And they actually gave you 2.8 million where you were required to upload the predictions for those 2.8 million where you were not told what the customer's rating was. But that set was randomly split. Half of it was the official test set that determined who was the winner, and then half of it was an unofficial quiz set where you were actually told your score on the quiz set, sort of as you from day to day, to get a sense for your progress. And those scores were displayed on a leaderboard, and anyone could go look at that web page and see where the teams ranked. But I think it sounds like we have a crowd of people that have a lot of background in data mining. As you know, those are the best evaluation of a model is on data that has not influenced it in any way, and that's why they designed it this way, so that you had a test set where you had no idea how you were doing. I mean, now statistically, obviously, when you have 1.4 million data points, or rather 2.8 million drawn from the same distribution, randomly split, should be very, very close. But when you're dealing with such small margins between the teams, there could be some sort of subtle overfitting going on there, and so that's the way that's why they did it that way. Yeah, so that's how it worked. And then each data point is very simple. It was just customer ID, it's sort of an anonymized customer ID, and the movie and the rating 1 through 5 stars, and that was just integer valued. But of course, your prediction could be real valued. You could predict 3.4 stars, for instance. And then they told you the date that the rating was made. And there are about 500,000 customers in the database and about 18,000 movies. So quite a large and high quality data set. And the evaluation metric it was fairly straightforward, just root mean squared error. And just, I think probably everybody knows what that is, but it just sort of tells you how off you are on average in some sense by in your prediction versus the actual rating. So their own system at the start had an RMSE of 0.9525, and then to win $1 million, you had to reduce that by 10%. So you had to get to 0.8572 or lower to qualify for the $1 million. But even if you hit that point, that didn't guarantee that you won, and I'll get into that in a little bit later. Yeah. Yeah, actually, I have that right here. Yeah, it's a little over 1. Actually, that's a very appropriate question. It sort of leads into the next point I wanted to make, which is when people hear, oh, you improved it by 10%, that doesn't sound like a whole lot. What's the big deal? I just wanted to point out that if you look at it in different units, it's actually a bigger improvement than that. So I think a lot of people are probably familiar with the concept of R squared. And if you, instead of looking at root mean squared error, if you look in sort of variance units and R squared units, their system was at R squared about 29%, and the $1 million barrier was 42.5%. And so to get there, that's almost 1.5 times the R squared that it was at before, right? So that's, when you look at it that way, it's a bigger deal than it might have seemed at first. And I should also mention that Yehuda Koren, who was one of the guys on the winning team, he did some experiments that indicated that when you look at how good your the recommendations at the very top, so in other words, if you rank the entire catalog, if you look at how appropriate those top few movies are for the customer, it makes a bigger difference than people realize just from how much the RMSE improved. So I think it was a bigger deal than some people think. Yeah. Well, yeah. Well, Stan Lanning is here. I think it's just because it was straightforward. I think. It's just. I think what you're getting at is that, as I guess, sort of as I was saying, you could look at, you could rank a whole catalog and say how good the top few of them are. Yeah, I think my guess would be just sort of logistically that was difficult, but they're just to run a competition base. It may have been less intuitive for some people, but I don't know actually. But yeah, certainly you could have used other metrics. Yeah, in any event. So let me just get some terminology clear as I go forward in the talk. So you're going to be talking about basis points of improvement, and just coincidentally, just because the RMSE is sort of order 1, the just 0.0001 or 1 in the last decimal place actually corresponds to 1 basis point in the sense of 1/100th of 1%. So you could very closely, not exactly, but very closely, and so you can kind of use those sort of interchangeably. You'll hear me kind of go back and forth between customers and users. That's just the same thing. And then you'll hear me talk about blending. Most of the Netflix competitors would talk about blending. But if you look at the machine learning literature going back a couple decades or so, that's really often called stacking. There's a paper by David Wolpert, who was actually my former boss at Ames, that was kind of a seminal paper about this kind of stuff. And so yeah, I'm just going to use these terms pretty much interchangeably. Okay, so this is sort of I kind of hacked the HTML of the leaderboard here, but this is what the leaderboard worked, except that I don't really remember where everybody was, so I've sort of dashed out a lot of the teams here. But as I said, I quit my job summer of '08, and then I was sort of just hacking away on this problem for several months on my own, and I did okay. I made some progress, but given that I didn't have a job and I had a PhD, I felt like I should have been doing better. But I got up to sort of the low 40s, and on my own. And so my own team name was Expensive Lunch, and I wonder, can anybody explain what that where that name comes from? Expensive Lunch? Anyone? Okay, so anyways, there are these theorems of machine learning called the no free lunch theorems, which say, I'm sure some of you may have heard of them. Sort of the gist of it is that no machine learning technique works well universally across all possible problems, and that you need to sort of capitalize on priors and so forth. And so that's where that came from. But anyway, so I was down there in the 40s. It was okay, but I wasn't thrilled with my progress. And then these guys, BellKor and Big Chaos, which is some AT&T guys, and then some master students in Austria, they had won the second progress prize, and they were in first place as of about the beginning of '09. And then this new team popped up. They called themselves Grand Prize Team, and they had an interesting proposition, and this is the team that I ended up on. That was half of the ensemble, so I have to say I really enjoyed working on Grand Prize Team. I love working with all those guys. The only thing I didn't like, I wasn't thrilled with the name, which was I think it was a little over optimistic, as we saw. It was not actually the Grand Prize Team, but what they offered was, okay, they said, all right, we're already 9% at 9% improvement, so we're at 90% of what we need to win the prize, but the progress towards the end was so slow and so tough that they said, you know what, we'll just take a third of the prize if we end up winning from having gotten a 9%, and the remaining 2/3 we'll give out to other people who help us get to that $1 million barrier. And so if you work out the math, the deal that they were giving, just 1 basis point of improvement was worth almost $7,000 in the event that they became the winning team. So that seemed like a pretty good deal to me. And so that got me more interested. And so I ended up sending them this blending technique. And that's the blending technique is the subject of this talk, and I'm going to get to later, in hopes that it would actually help them. And in fact, it did. It helped them quite a bit. Just sort of straight away, it boosted them about 13 basis points. And I don't remember exactly, but they moved up from like 9th to 5th or 6th pretty much straight away. So 13 basis points, all of a sudden I was on one of the leading teams and I had some sort of fairly serious skin in the game, and I was kind of more motivated from that point on. And so I kept kind of hacking away at it more intensely at that point. And then I remember maybe around April or so, the leaderboard looked like this. You know, I kept pounding away, and then we recruited some other people that added to our score. And yeah, at one point we were really just 1 basis point behind the leaders. And again, it was these BellKor and Big Chaos guys, and then Pragmatic Theory. These are two engineers out in Quebec, and they're superhuman as far as I'm concerned, because they were holding down full-time jobs and raising families and still winning the Netflix prize. But we were right behind them. And then I also want to mention Dace, and his real name is Larry Luo, and he ended up after the competition at Google, but I think he had the best score of any single person team, and I feel like he didn't get the mention in the media that he deserved. But anyway, so he was right behind us. But so anyway, so we were right on their heels, and then maybe as of late June, Pragmatic Theory had made a little more progress, and they were alone in first, and we were 12 basis points behind. And so they were only 19 basis points from the barrier, but progress was so slow that in my mind I felt like, oh, I still got plenty of time. And I wasn't sweating it too much. But then came like a day that was tough on me psychologically. And actually, just coincidentally, it was almost exactly 1 year, 1 year to the day, 1 year ago. So this is sort of like the 1 year anniversary of the breaking of the $1 million barrier. So these two guys, these two teams teamed up, and all of a sudden one day they had broken the barrier. But that didn't mean that that they had won. Once somebody broke the barrier, then there were 30 days left, and then other teams had a last chance to try to catch the team that had broken the barrier. And so I was pretty despondent at that point. I just spent about 10 days or so working on something that had improved us by 3 basis points, and then now we were 36 basis points behind. So that didn't look very good. But on the other hand, just sort of kind of the end game strategy was the way things played out was that there were all these other teams where this was their last chance to do anything, right? They'd all been working very hard and had pretty good solutions too. And so they were definitely incentivized to sort of team up, and that's what happened. And so not everybody, but sort of the majority of the other teams in the top 40 or so teamed up, and they formed another team that was sort of the second half of the ensemble. Grand Prize team was the first half of the ensemble. And actually, we made quite a late charge. And at the end of July, the final bell for the final submission rang. And then the quiz leaderboard, which is the only thing that was available to the public up to that point, ended up like this. And as far as the quiz score was, we were actually on top by 1 basis point, which was very exciting, at least briefly. Very
exciting in any case.
Yeah, it was exciting. But actually, as it turned out, just like right after the bell ended, well, we always knew that the test RMSE wasn't necessarily in sync with the quiz one, so we knew that this didn't necessarily mean that we won. And just a few hours after the final bell, BellKor's Pragmatic Chaos got notified by Netflix and said that they were sort of the leading candidate to win the contest. They still had to get their code verified and so on, but we knew at that point that we had probably lost. It made for some awkwardness. Like the New York Times got it right. They reported from the start that the BellKor guys had probably won, but there were some sort of smaller blogs and media that thought that we had won, and we were told to not explicitly say that we had probably lost, and so that was a little tricky. But anyway, it all got sorted out in September when they had the award ceremony. And so by September, it was revealed what the actual official rankings in terms of the test RMSE was, and it turned out that, well, it was only measured up to 4 decimal places, and up to 4 decimal places, we had tied them, and we lost because we had submitted ours 20 minutes after they had. So that was a tough loss, as we say in the sports world, but I got over it. I mean, I think honestly, I think these guys deserved it. They they had published a lot more than we had because they had won the progress prizes along the way. And so I think it was safe to say that we had more of their stuff in our solution than vice versa. But anyway, I was glad to have done well at least. Okay, so that's just like a quick summary of what happened in the competition. And as I said, what got me on the team and got me actually a pretty big share of the potential prize was a blending technique. And as far as I know, anybody who was high up on the leaderboard took the approach of building a wide variety of models and then blending them all together using a sort of a second level learner that learned to combine the outputs of the individual models. And as I was saying, that within the Netflix community, people were using the term blending, and I think they maybe just they weren't familiar with the academic literature that much. But if you look at the literature, there's a technique called stacking that is actually fairly well known that dates back to the early 90s. And I think, honestly, I'm sure there are examples of blending of models that go back even further than that. But this was certainly a very influential paper by David Wolpert. So I'm going to describe this blending technique. But before I get into that, I need to at least kind of briefly describe some of the major, if you will, first level models. Because in order to understand the blending technique, I have to kind of make reference to some properties of the individual models. So there were all sorts of different models that were used in these blends, but I think if I had to sort of pick three classes of models that were most prominent, these would probably be the three. So there were, amongst the most prominent models, there were nearest neighbor models, SVD models, or sometimes known as matrix factorization models, and restricted Boltzmann machines. So let me talk about nearest neighbor models here. So nearest neighbor models use correlations or some other sort of measure of similarity either between movies or more generally products or between users or customers in order to try to predict the rating. And there are two main types. There's user-based and movie-based. And a lot of the early work on collaborative filtering used user-based nearest neighbors. And so the idea here is that you find someone or a few other people that statistically tend to agree with this customer, and you see whether they like the movie, and you use that to predict whether the customer in question is going to like the movie. And so that can work okay, but particularly on the Netflix data and other sort of large commercial industrial settings, that can be a little tough. So as I said, there are 500,000 customers, so 500,000 choose 2 is a big number, and that's a very big matrix of correlations that you have to compute. And most of those entries in that matrix are not informed by a whole lot of movies in common. So if you take a random pair of users, they're probably not going to have a whole lot of movies that they've both rated. And so the accuracy with which you estimate those correlations is not the greatest. And then the other problem is that they're hard to explain. The recommendations are hard to explain. So as I understand, a lot of e-commerce companies have found that the recommendations seem to work better if you can explain the reasoning to the customer. And here, like you could imagine, like, say, well, there's some dude in Idaho that usually agrees with you, and he liked this movie, but that's that's not going to work, right? So that for that reason, people I think are less inclined to use user-based nearest neighbors, and movie-based or more generally product-based nearest neighbors is certainly more common. And here you find movies that tend to generate the same reactions, tend to be statistically correlated, and if you like the correlated movies, then maybe you'll like the movie that you're trying to predict. And so then the correlation matrix, the number of possible pairs, is a lot more manageable. And so here I have a very rudimentary movie-based nearest neighbor equation. And I want to say I'm not sort of advocating this as what you would want to do. If you want to implement something like this, I would recommend going back and reading the papers by, particularly by Yehuda Koren, who developed a lot of sort of more principled nearest neighbor techniques. But just to give you the flavor, this is sort of a simpler thing, the type of thing that people were doing maybe a decade ago. So the predicted rating for a particular user, and then I is indicating the movie, would be some baseline rating that would be maybe like the average rating for the movie. And then you would take some sort of weighted linear combination, maybe a convex combination of the, this R tilde would be the deviation from the baseline mean rating for the user for correlated movies, and then you would weight them by how correlated they are. So that's a simple version of that kind of thing. So just as a simple side point, I thought it was interesting. I found that actually negative correlations were actually more significant than I think a lot of people realized, and they were almost as large as the positive correlations. You usually think about generating recommendations from positive correlations, but so some examples like Saving Private Ryan is pretty strongly negatively correlated with enjoying Sex in the City, and Harry Potter and Pulp Fiction were sort of negatively correlated. And so I built a model that was just solely based on these negative correlations, and I could actually do almost as well as the initial Netflix system that they had before the competition started. And so yeah, I would get a kick out of it if Netflix like has some messages like, since you hated Rambo 3, like, you know, you might like this Woody Allen movie or whatever. But they haven't taken me up on that yet. But so yeah, again, this talk is about the blending technique, so I'm just kind of skimming over the actual models. But yeah, the second sort of most prominent model, and this is probably, if you had to pick one, I think, that where you wanted to get a low RMSE, you'd probably pick something in this class. And so these are, in the literature, they're referred to as SVD, which stands for singular value decomposition, or sometimes people call them matrix factorization techniques. Matrix factorization is probably a little bit more appropriate because the way that you end up computing the parameters actually doesn't correspond to an SVD per se. And I'm not going to get into that now, but in any event, you end up representing the customers and the movies as real valued vectors. And then your predicted rating is just the dot product of the user vector with the movie vector, or just like in the nearest neighbor case, in some cases you might have some sort of baseline, like some sort of average rating that you're starting off with, and then the dot product would represent the deviation from that baseline. So the way that they're computed, it's strictly just a statistically generated model where it's trying to fit the data by modifying its parameters. And so there's no guarantee that the parameters of the factors actually mean anything. But in some cases, particularly when you use a small number of factors, it turns out that some of the factors are actually somewhat interpretable from a human understanding point of view. And so I'll just show a couple of the kind of factors that you get. So here's one factor that you get if you run maybe like an 8 or 10 factor SVD. And so you, like for a particular factor, you can rank all the movies along that factor and see which ones are at top and which ones are at bottom. And so for one factor, you get movies like Sleepless in Seattle and Steel Magnolias at the top. And then at the bottom, you get like Star Trek movies. And it's hard to talk about these sort of results without sort of like wading into various types of, I don't know, stereotyping. So I won't articulate what this factor represents, but I think you can kind of get a feel for what's going on here. So here's another example. There's another factor or another dimension where you get movies like Citizen Kane and Bridge on the River Kwai. And then at the bottom, you get movies like American Pie, like Dude, Where's My Car? Right, so that's sort of like a old classics versus whatever, goofy teenage movies dimension. So as you look at this, you might think, well, isn't this just like the nearest neighbor stuff where aren't you just saying that these are correlated and these are anti-correlated? And I'm sure that they are, but remember, since you have this user vector, the user parameter for this factor can indicate how much that user cares about this dimension. And so like if you were someone, like I think I'm sort of open to both of these types of movies, and so if the user factor for this were near 0, that would indicate that you're sort of indifferent to whether it's like an old school classic or like a teenage movie. And so that's one way to think about the difference between this and nearest neighbor techniques. And then restricted Boltzmann machines, they are fairly complicated, and I'm not going to get into them here, but they're sort of loosely inspired by actual biological neural networks, and they're elegant ways of representing joint probability distributions. But I think that's all I'm going to say, just for the sake of brevity. So again, in order to get the best score overall, what people found was that you want to build a wide variety of models that capture different sorts of effects, and that was generally more helpful than kind of fixating on one particular model and sort of endlessly optimizing that one single model. And so like, one of the examples that was one of my favorites was this is something that Big Chaos, which was the the Austrian guys that were part of the winning team, they built a model that was strictly based on what day of the week it was. So just based on whether it was Monday, Tuesday, Wednesday, and so on, it would make a prediction about what the rating would be. And as you might expect, it does very poorly on its own. But if you blend it into a suite of models, which might be already very accurate on its own, but if none of the other models have any concept of day of the week, then even though there's just some sort of tiny amount of signal here, when you blend it in, it boosts the accuracy quite a bit. I remember I think I got like 13 basis points out of this, and I was very excited when I implemented it. But so that's an example of like it's really about what's fresh in a new model that you're adding to the blend, rather than its sort of individual accuracy. So then the question, finally I'll get to sort of what I'm presenting that's sort of new. How do we blend these together? So let's say we have a collection of models, capital L models, G1 through GL. Well, the standard way to do it, and this is what was proposed in the one of the early stacking papers, and this is also what generally people used in the Netflix competition at the start, at least, was linear regression, which is old and tried and true, and you just take a have a coefficient associated with each model and take the dot product, and you get your overall prediction. So yeah, so even though that seems sort of like pretty elementary, actually a lot of people had trouble doing a lot better than this, particularly in the first year or so. Now, in the second and third year, I think people finally started to have some progress with some other blending models, and so people would try splitting up the problem into different regions depending on, for instance, how many ratings the customer had supplied, and doing different regressions in those different regions. And the insight behind that is sort of what drives the technique that I'm going to talk about. But yeah, that was sort of like an early effort along those lines. And then eventually people got some benefit out of neural networks and decision trees. And there's a particular type of decision tree that figured in the winning solution that they added kind of in the last year. And then as you look at this, there's probably a technique that people are looking for that is actually not up here that you might expect, which is support vector machines or other sort of kernel-based techniques. What seems to be going on was that people just had trouble with the scale when you were working with millions of data points. They had trouble getting support vector machines to work well. That's not to say that it's not possible to do it, but at least as far as I know, that among the leading contestants in the contest, I don't think anybody got a lot of benefit out of those, which is maybe a little bit surprising, because I think in a lot of situations, like SVM would probably be maybe the first thing you would try, or what you would bet on maybe. But yeah, it didn't figure so much in this contest. Okay, so let's get back to just linear regression here. So you have in basic linear regression, you just have a coefficient corresponding to each model, and then you just take your dot product. And so this is an example if you actually ran it on a data set of like what you might get, like a 0.48 times the SVD model plus 0.31 times the nearest neighbor model plus 0.21 times the restricted Boltzmann machine, right? So that's pretty straightforward. That seems reasonable enough, but you know, maybe we can do better. Why should those coefficients be static, right? So depending on other information, you might think that certain models should get more emphasis in certain situations and less emphasis in other situations. And so, so that was the insight behind what we what ended up developing. And so we're calling this technique feature-weighted linear stacking. And I should actually just say briefly, it's pretty simple stuff, and I think it's likely that someone has done something like this before. And so, I mean, it's hard to do a good literature search, I find, in this field, just because there are people from stats and CS and EE and different fields. They call the same technique different things, and so there's probably something out there that prior to this. But in any event, it was certainly not well known since no one was trying it 2 years into the competition. So, as standard blending, you just have the weight times the model. Well, what if you have other information, and that's what I'm calling these blending features, F1 through FF, that might tell you what the W should be in different situations. So as I think I mentioned before, some examples of that might be the how many customer ratings or how many movie ratings there were. So what can we do to make the W depend on these? Well, generally the first thing to try that tends to be sort of analytically elegant is to assume some sort of linear form. And so if we let the W be a linear combination of these blending features, and then we plug it back into this form that we had here, then yeah, it's just sort of very straightforward algebra. You just multiply it all out, and what you end up with is, once again, it's just a linear regression, except this time you're regressing on the products of the models with the blending features. And so if we have capital F features and capital L models, now we have LF parameters to estimate corresponding to each possible pairwise product of blending features with models. Right? So once again, it's just one big linear regression. And so this is a very sort of simple case that I've diagrammed here. So in a standard case, you just have the three models, and then you have a parameter associated with each one. In this case, if you had two blending features, you would take the product of each model with each blending feature, and you have a parameter associated with each product, and then you just run a regression on that. And so yeah, it's very simple stuff, really. And I'll just mention briefly, you can handle some special cases. Like you could say, well, what about, don't I still also want to regress against just the models by themselves? And then you can have a sort of a null blending feature that just takes the value 1 and accomplish that. And then you also find the blending features themselves have some value as inputs sort of taken independently, and then you could define a null model that always takes a value 1. And so you can handle that. Right, so how much did this help? So for grand prize team, we had 119 models, and this blending technique decreased the RMSE by about 20 basis points, which is, in some contexts, I'll be honest, is not very much. But in this context, where 1 basis point was worth $7,000 and there's a lot on the line, it was kind of sort of a fairly big deal. And just to give you some perspective, so just for my own blend, right, I was down in the mid 0.87s or so. It was a 35 basis point gain. And then if you just have 4 models, I just tried this really quickly. I just picked 4 models fairly arbitrarily. It was a 44 basis point gain. And that might be more reflective of a more reasonable situation where you're not obsessed over one problem for 3 years straight. But so as you get, when you've been working, or when large collections of smart people have been working very long on the same problem, it's hard to squeeze out extra accuracy. But I think you get a bigger boost from probably in other situations. So yeah, let me just go over what some of the blending features were. yeah, as I mentioned, the number of user ratings, number of movie ratings, and as you might expect, some models might do better depending on how many ratings there were. And so then another feature was the average number of user ratings for the users who rated the movie, right? So you might have a movie that got rated by a lot of users, but those users might not be users that have rated a lot of movies. So they might be, you might have ratings from a lot of users, each of which you don't know very much about, right? And so that's an interesting piece of information. The number 4 is kind of relevant for the nearest neighbor technique. So if you add up the correlations of all the movies that the user's already rated with the movie that you're trying to predict, if that's small, then you might expect that maybe neighborhood techniques, nearest neighbor techniques, might not be in the best position to generate a prediction there. And then number 5, I'll just actually do a quick plug for a technique that I developed, which was something I call ordinal SVD that actually generates a probability distribution over the 5 possible ratings, but is otherwise like basically an SVD or matrix factorization. And actually, I have some code on the Netflix Prize message board if you want to find that. But anyway, it can generate an uncertainty. It can tell you how uncertain it is about the rating, and that, as you might expect, that's a useful blending feature. Yeah. Many of them are, but they don't have to be. Like there are some of them. No. Actually, it's just one big linear regression. That's all it is, right? Because it's just you just take the product of each feature with each model, and then that's each product is an input, right? And then there's a parameter associated with that, and it's just one linear regression. You could chunk things if you wanted. That might also be interesting to try, but. Mm-hmm. Of which models helped and which didn't? Or, well, actually, so that collection of 119 was very sort of rigorously designed in that to get on the team, you had to submit a model that improved the score. And if you didn't improve the score, you weren't on the team and your model didn't make it into that collection. And so I don't know how many people sort of tried submitting stuff, because they actually had a server where you could upload your predictions based on a particular model. And so if you weren't careful about how you constructed it, there would be a redundancy. But this was that was really what Gabor, the guy in Hungary I mentioned, what he was in charge of. But he sort of was the gatekeeper, and so there was no redundancy in that collection of 119. If you pulled something out, you would lose at least a basis point, and usually more than that. But yeah, very good.
You mentioned it was regression. Was there anything like a stepwise regression that could kick models out or kick fields out?
Yeah, actually, that's something I'll mention at the end. Is sort of like future directions. I did a little bit of that right at the end of the contest, but I want to revisit it. But I think what you might be interesting to look at would be to kick out particular products of the features with the models, because I doubt it's really helpful or critical to interact every blending feature with every model. So yeah, so I was going to mention that at the end. Yeah, right. So let's see how I'm doing on time here. Yeah, let me just quickly go over a few more of these blending features. So you look at the standard deviation of the user ratings and movie ratings. That gives you a sense for how much information you have about the user or movie. Standard deviation of the dates over which the movie was rated. So a lot of the models in the second and third year modeled time effects, and so that's interesting to know whether the ratings of the movie were collected over a long time period or over a fairly concentrated time period. And then
when you say date, was it a time gap from when the movie came out to when the movie was rated, or what was? I mean, how was the date represented?
Yeah, I mean, it wasn't necessarily a how would I put it? It wasn't a gap from release. It was just a date in and of itself, and so then you just looked at you have a mean, right? If you have a collection of dates, you have a mean, and then you just have a standard deviation of dates, and then yeah, that was what that was. But and then the maximum correlation of the movie with any other movie. So you can ask, is there at least one movie out there that's correlated with this movie? That turned out to be a useful one. And there actually, yeah, there are quite a few more. Like I said, we ended up using about 25 or so. Let me just talk quickly about the computational cost of this. So yeah, you end up forming this matrix that's n by LF, and then you just solve a linear system. And then we actually used a little bit of regularization here, some ridge regression, right? I think probably most people are familiar with that. And so most of the costs generally, if you have a lot of data, is going to be in the formation of A transpose A, and so that's n f squared L squared. And so just to give you, it's always nice to look at the theory, but I think I also like to look at like sort of some concrete examples here. And so just to give you a feel, so if you use just a couple 100,000 data points, 26 features, 10 models, which I think is sort of industrial strength in a lot of contexts. It's just, yeah, it's very quick, 90 seconds, right? But if you have maybe 120 models, 1.4 million data points, that was demanding. And so I'm not much of a multi-threaded programmer, but I learned some multi-threading at the end of the contest and was hacking away on an 8 CPU Amazon EC2 rental. So yeah, so it can get pretty expensive, but there's some tricks that you can do, and I won't dwell on this too much, but if you have a blend that you're maintaining and you're periodically adding new models to that blend, you can serialize the matrix to disk and then load it back in, and then if you're testing out a new model, all you have to do is just compute a few rows and columns corresponding to the new model, and that can save you quite a bit of time. And the same thing goes for the new blending features. And so, yeah.
Perhaps this ties into the scalability discussion as well. But to me, this looks like you have for each model, you're just treating that the results of the model as a feature, then you're adding some blending features. So you have a reasonable number of features from the model evaluations, a reasonable number of features which is the same for the blending features. And so then my question is, you do some sort of a, not convolution, but some sort of a combination.
Right, yeah.
Why not just reducing your regression problem altogether and use your favorite regression fitting feature combination type of blending?
Yeah, so you're saying rather than take all pairwise products, why not sort of add them selectively, see which ones are helpful? Is that?
Why not
Yeah.
reduce combined features, by crossing model or feature?
Oh yeah, no, actually, yeah. You could get a little bit of boost out of taking some quadratic interactions of models actually, and there was, I think, like there was a point at which that helped it, but there were a lot of things like that helped at one point, but then as you kept adding stuff, then they kind of dropped out. We pruned them out, but yeah, interacting models with models was useful, and I think we did. We did play around with interacting the features as well. So yeah, I mean that's definitely, yeah, you could explore that as well, certainly. Yeah. So let's see what I'm doing here. Yeah, and I just wanted to mention that another reason that I think this is kind of useful is that unless you have one of these gargantuan model collections, as I said, it runs pretty quickly, and it's just kind of a quick way to generate these features, which may actually be useful for as inputs to more complex blenders like a neural net or decision tree. And we actually did some of that. So we found the features by this linear technique, and then we fed them back into a neural net as inputs alongside the models, and then let it see what kind of more complex nonlinearity you could find, and we got some boost out of that too. So that's another benefit. And so then one of the things that I wanted to, I really wanted to sort of demonstrate this more myself, but I think at least in theory this should be useful in context other than recommendations in collaborative filtering, and just in just when you're blending or stacking models together in other situations. And I haven't spent as much time on this as I would like, but just this morning I just kind of quickly downloaded some U.S. Census data from, this is from the UC Irvine Machine Learning Repository, and there the task is to predict if somebody makes more than $50,000 based on other demographic variables. So I just did a really quick nearest neighbor model, and this is a classification error rate. And so the nearest neighbor model is a little bit better than the logistic regression model. And then I just did a simple kind of standard linear regression blend, and I got that I couldn't improve upon the nearest neighbor model classification accuracy that way. But when I added a little blending feature, which was just the average, average distance of the neighbors to the input vector to be predicted, right? So if that's large, then you might think a nearest neighbor model would be less reliable, right? If the most relevant neighbors are not that similar. When I added that in, I did squeeze a few basis points out. Now this is just like 2 or 3 hours of work, so I wouldn't read too much into it, but that was encouraging to me that I tried it out on a different type of problem, and I got at least a little bit of juice out of it. So some of you may be asking, so what's so great about blends, like especially if you're working in a commercial setting, like what am I going to do with this gigantic collection of models? Like I'm never going to be able to maintain this, and like I'm never going to be able to debug it. It's totally impractical, and there's probably something to be said for that. But I just want to point out that even if you were concerned about that, that it may be worthwhile to still build blends because, well, number one, they can tell you, they can give you an upper bound on what kind of RMSE, or whatever your prediction evaluation measure or metric is. They can tell you what's possible, and I think people have found, just like in computer science theory, sometimes like you have an existence proof of or even mathematical theory, existence proof of a certain solution. A lot of people find once somebody comes out with an existence proof, then within a couple of years or maybe sooner, usually somebody comes out with a actual concrete solution, and there seems to be some sort of psychological effect. Like once you know it can be done, then that helps you actually do it. So these blends have inspired the design of individual models that are much more accurate than what anybody had previously. And so, just to give you a feel for that, so, the solution that won the first intermediate progress prize in 2007 was, I actually don't know exactly, but it was on the order of 100 models, and that got 0.8712, and that won the prize. But the pragmatic theory guys, the guys from Quebec, as part of their grand prize winning solution, they had one model that equaled that accuracy by 2009. Now that's that's not the most concise of models. If you go and look at their write-up, that model, it takes up probably more than half of a page, all the parameters involved in it. But still, it's one minimization, boom, you're done, and you have very, very high accuracy. And so that's an argument for using blends even if you don't anticipate having them in a production setting. And so just thought I would point that out. So let me just just kind of sum up with just like some merits of this technique. And I think one of the biggest things is it's very easy to implement, right? Linear regression is just not very hard at all to get working. And I would contrast that to a lot of the nonlinear blending techniques where you train them iteratively, something like a neural net where you have step sizes, and it depends on your initial parameter setting, and you're never sure if it's done, if it's converged or not, and they can be a pain. Linear regression, right? It's exact. It's analytic. You know exactly how long it's going to take. You have the the optimal, at least the optimal in-sample parameters when you're done, and so there's a lot to be said for that. And I haven't done a lot of work on this yet, but potentially at least you could interpret the results, right? So that's one of the other things about linear regression. You could just look at the weight associated with each model, and there you could kind of clamp the blending features. You could say, all right, if the number of customer ratings is high, how do the weights on the different models look versus if the number of customer ratings is low, and that may give you some insight into the sort of strengths and weaknesses of the models. You have to be a little bit careful with that because when you have models that are highly correlated, or what statisticians call collinear, interpreting those parameters can be a little bit dicey. You want to be careful about that, but potentially you could get some insights from that. Yeah. So then, yeah, as I mentioned, I want to look at additional application domains. I think it should be useful outside of recommendation systems. Yeah, I guess as somebody mentioned, there's probably no reason to interact every model with every feature. And I did a little bit of work along those lines, but I want to do some more work on doing some more principled selection of the interactions. And then Lester, one of my teammates, he's done a little bit of work on trying to fit the blend with a non-negative weight constraint. So that might be sort of more intuitive to constrain the weights to be non-negative, so you're taking some sort of convex combination of the model. So those are all possibilities. So I guess before we go to general questions, I had like a fun little, I hope it's fun anyway, a little demo to that's actually not directly related to this blending technique, but just as I was talking about how you can look at the most correlated movies and the least correlated or most negatively correlated movies with a particular movie. And so if we could switch the system over to Linux. And so, yeah, so let's see, what do we got? The Miracle Maker, right? Jesus of Nazareth. Yeah, I don't know if people know the Left Behind series, but that's a sort of I don't know how to describe it, like a Christian action series. And then, yeah, Michael Moore movies are negatively correlated with, and like an anti-Robert Rupert Murdoch, yeah. That makes sense. So I don't know if yeah. So we could do. I don't know how much time we have, but we can do a few more of these. Yeah. Tron. Okay. Oh wow, that goes way back, early '80s. Let's see if they have it. The problem with that is that the N key stopped working on my keyboard, and so let's see if I can. I have to cut and paste the N in, but give me a second here. Yeah, I think I'm having trouble on Linux, so maybe we can save that one for later. So let me revise that. I guess if you throw out titles that don't involve the letter N, I can do it. So yeah, we'll do that. I'll do that for you later, but maybe 6 cents. Okay. I think I can. That's specific enough that I can bonus material. I guess. Yeah. Okay. Yeah, so let's see. So Unbreakable and Signs. Those are other M. Night Shyamalan movies. And then that's interesting to see. Three Stooges, Sanford and Son. Kids in the Hall, I would not guess actually, but Three Stooges. Maybe it kind of makes sense. Yeah, some of them are kind of mysterious. The negative ones, but I think sometimes the negative ones make a lot of sense to me. But so yeah, I don't know. Maybe one or two more, and then I can do general questions. Eyes Wide Shut, okay. Oh. 8015. So let's see. Oh, did I do it? No, I got it right. Yeah. Yeah, there's like an off by one in this file versus what I put in here. But yeah, Eyes Wide Shut. So Magnolia. I think I remember that movie. Mulholland Drive. Clockwork Orange is another Kubrick movie, right? Barry Lyndon is a Kubrick movie. And then the negative ones, I think, yeah, Passenger 57 and U.S. Marshals are sort of like, I don't know, sort of just straightforward macho action movies, I guess, which kind of makes sense. Armageddon, yeah. So,
It's a planet, straightforward.
yeah. So, Then I don't know, maybe one more, and then I'll just do. Usual suspects. Okay. All right.
And after that, maybe the Matrix.
Okay. All right. And then yeah. Well. I guess I mean I don't know how much time we have, but we can go do as many as people want, I guess. But. Yeah. Wow.
And after that.
I think that violates the terms of the data, actually. But so Usual Suspects, yeah, Memento, Pulp Fiction, Fight Club, Little House on the Prairie is I can see that it's negatively correlated with the Usual Suspects, Pearl Harbor, yeah. And then you wanted the Matrix, I guess, or
yeah.
Okay. Right, and so then, yeah, the other Matrix movies. And then negatively, yeah, Steel Magnolia, Pretty Woman, Sweet Home Alabama, negatively correlated. Dirty Dancing, I can see that. So yeah, I mean, I don't know if, like, we can do more of this, or we can have general questions, or we can just finish, or whatever people want to do. So, yeah, you gotta. Well, I think I never really completely gave up on one or the other. It was sort of a back and forth thing. Just once I had this general framework for this blending features technique, that was kind of always a background thing. Like if something else was running, or if I was just kind of feeling tired, I would just take a break and so I wonder if this blending feature works. And that's one of the nice things about it, is that it's really not a lot of labor, right? So usually even just a few of them took some work, but most of those blending features are very quick to code, and so you just try it out, look at the cross-validated error, see if you get a little boost. And so yeah, it was just sort of back and forth. I didn't really I sort of abandoned one. Yeah, I mean, for sure, people tried all kinds of different things. Yeah, for sure.
Sounds like you were combining models after they were out. Did you know of other people that tried, like, doing a decision tree up front to subdivide the data, and then do like one model per leaf of the tree? So in other words,
yeah,
that way the models would work on subsets.
Right,
of data
in different regions of the data. Yeah,
or
I'm sure that people did some of that. Like, just off the top of my head, I can't think of concrete examples, but so yeah, I don't know if there was anything really prominent along those lines, but it may just be like a blind spot in my knowledge of the literature. But oh, okay, yeah.
Talk about problems in the data set that you were given, anything that, is there any clustering or holes in the data that you have to work around?
When you say holes in the data, do you mean like missing values or things like that?
Or maybe that one user was overly prominent.
Yeah, well, so for sure, one of the things that was hard was that and I think this was maybe just what the Netflix's business objectives were, was that the test data, every customer was equally represented, so that the last 9 ratings of each customer form the test data. But in the training data, some customers had rated thousands of movies, and then other customers had rated just a few. And in fact, even less than 9. And so if there were less than 9, they would just, whatever there were, like a certain subset of the handful would be in the test set, and then maybe you just have like 3 or 4 in the training set. And that made it tough, and I actually that was one of the first things I tried, was to try to sort of correct for that, the distinction between the training distribution and the test distribution, but I never got really much benefit out of it. Now I've spoken with other people who seem to think that who I guess according to their own experiments did get some benefit out of capitalizing on the fact that the test distribution is not the same as the training distribution. That was something that I probably spent too much time on and got kind of frustrated on. But my intuition says that that should be important, but I didn't capitalize on it the way that I wanted to. So, yeah. Yep.
Some users gave grades 1 through 5, and some of them just gave 2s and 3s or something like that.
Mm-hmm.
What did you do to normalize?
Yeah, so there are all sorts of techniques that would subtract out certainly the mean user rating. And then I think I mentioned that a little bit. You would work on the residual of the mean user rating, or actually really the more sophisticated models would pull out the user and the movie mean, and there were actually several other examples of what people call global effects. So a global effect was pretty much anything, any sort of prediction where you didn't have to know the specific identity of both the user and the movie. And so you could find other trends like, I don't know, maybe certain users tend to like older movies or newer movies, or certain users, certain movies tend to be more popular amongst users who rate a lot of movies and things like that. And so there was a lot of sort of normalizing by subtracting out all these global effects and then working on the residuals of those, for sure. Something that I worked on a little bit and that I expected to have more benefit than that actually did was to also normalize the sort of for the standard deviation of the user rating. So you can imagine some users, they never go beyond 2 and 4, and then others are like, have strong reactions, they're like 1, 5, 1, 5, right? And I did a little bit along those lines. I don't remember actually boosting the blend very much, but my intuition said that you should be able to capitalize on that. So yeah, so there was definitely some work along those lines. Yeah.
So one of the competitors was somebody had rated a bunch of movies, applied for that particular day, a couple of days, or movies. Did you want to work in that area?
Well, so one of the guys that I worked with who actually got an article written about himself in Wired magazine. There's a guy by the name of Gavin Potter who's in England. He is a psychologist, although when I first read that I was like, wow, this whatever this right, something this like just pure psychologist is like doing this amazing computer science hacking. But actually he had done operations research, so he was a pretty technical guy too. But in any event, so he did a lot of work on trying to sort of account for different psychological effects. And so I would just Google the name Gavin Potter, and you'll sort of read what he has to say about that. He actually has a blog, I think, where he still has some things to say about that. But certainly one of the important factors that people found, people developed in the second and third years was to correct for, I guess as you were saying, like an average user rating for a particular date. And that might be that someone was in a good mood on that day, or it could be that there were actually multiple people using the same account, right? And so maybe the husband gives high ratings and the wife gives low ratings, and so you want to correct for that. And so yeah, there was definitely some work along those lines, and I didn't invent a lot along those lines, but I definitely capitalized on what other people had done and was published. Yeah. I think that's a question for this guy, I think, rather than you. Okay. Yeah.
Is that just for the publicity, or?
Yeah, I can't say, but the indications are that they were pleased with the results of the contest, and it was as you saw, they wanted to do a second one, and then there were some complications. But,
Any thoughts about as new movies come out, how to update the system, or as new users are added to the system, how to handle with updating the models? You know, retraining the entire system versus partial retraining?
Yes, that's a good question. Some of the techniques are sort of more elegant about that than others. To be honest, I haven't done a lot of work on that. Simply because I haven't been. It wasn't required for the contest, frankly. Like I haven't worked on it in a commercial setting, but that's definitely I'm sure in a production setting that's valuable to do sort of incremental updating of the parameters. But it can be, depending on the model, it can be tricky. I'm sorry. How would you cheat the system again? By
I think since the data already occurred and they weren't adding new data to it. Yeah.
Oh yeah, it was just a one-time snapshot as of I don't know, end of 2005. They collected the data, they started the contest, and then you downloaded the data starting in 2000.
Time travel, then it's probably okay.
For the purposes of the contest, it was just this one static data set. And so, yeah, it was data collected up through 2005, and then the last 9 user ratings for each user, that slice was the test and quiz set. So, yeah, for the purposes of the contest, there wasn't too much of a concern there. Yeah.
I'd be curious, and directed towards him, if someone has taken all of these and run them against, say, next year's, you know, how fit is this to the training data you had? How well, I mean, do they stay in the same order if you run it against 2006?
Oh, I don't have 2006's data, so I don't know. Yeah, I mean, I think, well, what I can say that's sort of germane to that is that, which I think I mentioned briefly before, was that one of the big advances in the second and third year of the contest was to model time effects, and there were that sort of gave us a significant boost, and the $1 million barrier I think certainly would not have been broken without modeling time effects, and so there were some pretty clear. Well, I think I already mentioned, like, you know, people were in better moods on certain days or other days, but there were effects like certain movies seemed to get higher or lower average ratings depending on a certain month that you were in, and then there were long-term user trends in something that would sort of slope over a period of months in terms of the mean user rating, and also even in a more sophisticated way in terms of their taste. So we talked about that SVD vector for a user. So there was some accuracy boost from having kind of a time slope to even that taste vector. So maybe you were into certain types of movies, you know, in 2004, and you gradually lost the taste for that, which, you know, reflects reality. So yeah, that's about as much as I can say, is that I know that time effects were important. So yeah.
It sounds like essentially one training set and test set. How do you bring over the entire contest?
Well, I mean, I think what was well designed about it, which I think I mentioned, was that while the contests went on, the only feedback that you ever got was on what was called this quiz set. So again, they had 2.8 million ratings that potentially could be part of the test set that determined who won, and they split those randomly in half. Actually, they actually had 4.2 million ratings, and they split them into 3 subsets. One of those 3 subsets, they gave you the ratings for them, and then that was just kind of, they were just being helpful, where then you could test against that, you know, as much as you wanted. The quiz subset, they would only give you feedback once a day on, because you uploaded your predictions to the server, and they tell you, okay, here's how you did on the quiz subset. But that did not determine who won. What determined who won was your score on the test subset, and all the modelers, all the competitors like me, we were not told what our score was on the test subset, and so just by construction of the contest, we had no feedback, and so it was a real, like, true, proper test set in that sense, and so you couldn't overfit it, right? Because you were never told how you were doing as the contest went on. And just after the final bell, they said, "Okay, now here are all your test scores."
You couldn't overfit it. It's a static test set.
I mean, it's static, and yeah, I mean, I guess if that's
You couldn't overfit it because you didn't retrain on it.
right, yeah.
But you could argue that the final results, especially since they differed by so little, might be arbitrary.
Arbitrary in the sense of you mean like working on that particular data, but not in the future, or
If you do 1,000 tests on the same test set, sometimes you can get effects of just what naturally memorizes to the test set. I think is what you might be getting.
yeah, I mean, if you did 1,000 tests on the test set, but again, that was
Yeah.
the contest was structured so that you couldn't do that.
Right.
But I mean, so certainly, I'm sure, yeah, it's not obvious that the models, if you would just use them through 06, 07, 08 without refitting them, they might not do that well. But yeah.
We have time for one more question.
So you mentioned you're interested in having recommendations that can be explained, and you talked a little bit about the comprehensibility of the models and doing the blends. I'm curious how you feel about content-based recommendations.
I'm sure that one of the virtues of content-based recommendations was that they are somewhat explainable. I think, but what was sort of surprising in the Netflix prize contest is that a lot of people tried to get an accuracy boost out of them, and nobody, at least among the leading competitors, actually succeeded at all. And that doesn't mean that in other contexts, content-based systems aren't very helpful, but in this particular problem, I guess partly just because you had so much data, it's just the data spoke better than any sort of tags about, like, whatever, horror movie, romance movie, who the actors were. So I think that was one of the big surprises, actually. You couldn't crawl their site, but some people still, they reported trying to use different tags. Yeah, and they said I tried and I didn't really get anything out of it. So.
Thank you so very much.
Sure.